Question 3. Reaction 1 shows the decomposition of the hydrogen peroxide to form the water and oxygen. A part 1. Define entropy. Entropy is the measure of disorder of a system. Means when the system is more random or more movement, so the entropy is greater. Especially when the reaction involves the gases, the productions of gas molecules. So for example, in reaction 1, we know that liquids form liquids and gas particles. When a reaction forms gas particle, so we say that it's produce a more random or more disordered particles. The movement is greater, so therefore the entropy is greater. So the definition is very easy. Just a measure of disorder of a system, means how random is the system. Or you can actually explain in terms of numbers of possible arrangement of the particles. More arrangement, higher entropy. Part 2. Predict the sign of the standard entropy change in the reaction 1. So it must be positive because it's from liquids at the same time from gas. Whenever it's from gas particle, it must increase in the entropy. So therefore it's positive. So the explanation is very easy because the gas particles form. Another possible answer is this. More moles in products because it's 2 mole from 3 moles. However, the gas particles is still the major consideration. Whenever gas particle form from solid or liquid, so the entropy it will be greater. Part B. Some bond energy data given in this table 3.1. OO bond, OH bond, OO double bond. Okay, use this data in table 3.1 to shows that the enthalpy change of the following reaction is negative 196 kJ per mole. In order to do this, you have to use the bond energy and you must know the structure. For the H2O2, its structure is this. Means in this structure we can see that it has 2 OH bond and 1 OO single bond, and it's 2 moles here. Therefore in this part we need to use the correct numbers of bond and types of bond. So we need to use 1 OO single bond energy and 2 times of the OH bond energy, which represent the H2O2. And you must know how to times 2 because it's 2 mole. Here need to times 2. Minus is actually for the products. Products, because it's the bond formation, is released energy. The minus sign here is actually the energy released from the bond formation. For the product, we know that it's from H2O and the O2. H2O, we know that in the structure, it has 2 OH bond and 2 moles here. Therefore, it's going to be 4 bond energies of OH, total 4 bonds energy. Okay, 4 times of the bond energy of OH, okay, plus the bond energy of OO double bond because it's oxygen molecule. Okay, substitutes all the values inside this. Right. Okay, therefore you get negative 196 kJ per mole. Part C. Some standard entropy are shown in this 3.2, and the reactions equations given. delta H is given, delta G is given. And now it's want you to calculate the standard entropy, means the molar entropy of oxygen. So get this one. Okay, first, you need to know how to get the delta S in the Gibbs equation. Delta S, we need to use the molar entropy of the products, the sum of the molar entropy of products minus the sum of molar entropy of the reactants. This is how we get the delta S system, means this one. Okay, of course, when you start to calculate this, you must know the Gibbs equation because it's 1 mark. So delta G equal to delta H minus T delta S. So this one no choice, you must memorize. And substitute the delta G's here, delta H here, because it say that this one is the standard entropy and enthalpy and Gibbs, so the temperature must be the standard temperature, which is 298 Kelvin. And this part you need to know how to get it. I already told you just now. Okay, this is the delta S system. So we use the sum of the entropies of the products, which is this one, H2O, and the O2. So this is what we need to get. Okay, minus 2 times of the entropy of the hydrogen peroxide. Okay, after that, when you get this relation, means almost there. But before that, you have to understand the delta S, when it's used in the Gibbs energy, the entropy need to divide by 1000, because entropy itself is joule per Kelvin per mole. So when it's used in the Gibbs equation, it need to divide by 1000. So you need to put the 1000 here. Okay, after that, you rearrange, then you will get the molar entropy of the oxygen, which is 205 joule per Kelvin per mole. For the part D, decomposition of the H2O2 aqueous is catalyzed by the aqueous iron 3 chloride and by the silver metal. Identify which of these two catalysts is acting as homogeneous catalyst. Homogeneous, we know that the catalyst must be in the same phase with the reactants. So we know that the iron 3 chloride solution is aqueous, H2O2 also aqueous, so they're actually in the same phase. So homogeneous catalyst now is the aqueous iron 3 chloride. Okay, explanation is very easy because the catalyst now is same phase as the reactants, and the reactant is H2O2 aqueous. For part E, 2 half cell given, and the E0 half cell also provided. And for this part 1, an electrochemical cell is constructed with the following half cell: acidified solution of H2O2 with platinum wire, which is this one; chromium 2 mixed with chromium 3 with platinum wire, which is this one. Identify the positive half cell and calculate the E0 cell. So this one you have to use the electropotentials that are given, and you need to find out which one is more positive. Obviously, the hydrogen peroxide half cell is more positive. When it's more positive, then we know that it's more likely to gain electron. Means it will stay as reduction form. When it stays in reduction form, means it gains electron. When it gains electron, we know that it's undergo reduction. Reduction means it's a cathode. And when it gains electron, it's actually telling us this one is a positive half cell. And of course, the chromium 3 and chromium 2 half cell here, it need to be the oxidation half cell, means it need to reverse. The chromium 2 now need to oxidize to chromium 3, release electron, and this electron is gained by the hydrogen peroxide half cell. So when this one is undergo oxidation, so we call this one as anode. Because it's produce electron, this half cell is the negative half cell. So it's very clear that the positive half cell now is the H2O2. To calculate the E cell, we need to use the E cathode minus E anode. So we use the potentials that given. 1.77 minus negative 0.41, we get positive 2.18. So this is the E naught cell. For part 2, calculate the value of delta G for the cell reactions that occur per mole of H2O2. So we need to make sure it's 1 mole of H2O2, and now it reacts with the chromium 2 and 3 half cell. From here, we know that 2 electrons involved. So therefore, the N, it must be 2. Of course, first, you must know the equation, means the equation between the Gibbs and the E naught cell. So is delta G equal to negative NF E naught cell? This one you must remember. So this is the relations between the Gibbs and the E naught cell. So the N, now we know that is 2 electron, means N is 2. The Faraday constant is 96500, and the E naught cell is just calculated is 2.18. So therefore, we know that the Gibbs now is negative 420.740 joule per mole. But we not really give the answer in joule per mole. The unit should be kilojoule per mole. Okay, after you use the negative NF E naught cell, you get joule. Therefore, you need to convert it to kilojoule, divide this one by 1000, you get negative 420.7. So this is the answer. Okay, so for part F, the E naught cell for the hydrogen peroxide, okay, is given. Copper 3 and copper 2 half cell is given. Now, an electrochemical cell is constructed with the following half cells. Okay, the half cell 1 is the acidified solution of H2O2 under standard condition with platinum wire, which is this one, the first one. Okay, so therefore we know that the potential is same as the standard potential, which is 1.77 because it's standard condition. But for the half cell 2, now it's not under standard condition because the concentration now is not 1 mole per dm cube for both. So the chromium 3 now is 0.02 and the chromium 2 is 2 mole per dm cube. So we need to calculate the E, means the E cell, the potential for this half cell, because now it's not going to follow 1.82, it's going to change because the concentration now is changing. So therefore, for part 1, use the Nernst equation to calculate the value of E for the electropotential of the half cell 2, means this one, the second half cell. And of course, you must know how to use the Nernst equation. So E equal to E naught plus 0.059 over Z. Z is the numbers of electron transfer. Okay, times log concentration of oxidized species over reduced species. So this is a Nernst equation that you must use. So this one is given 1.82 plus 0.059 over 1, because in this half cell it just involves 1 electron. Okay, times log 0.02, this is concentration of cobalt-3, over 2 mole per dm cube. This is a concentration for cobalt-2. After that, you get positive 1.702. So this is the potential for the half cell now, okay, with the concentrations that given. And we know that it's actually smaller than the hydrogen peroxide half cell. Part 2. Write an equations for the cell reactions that occur in this cell under this condition. If let's say the reactions is happen under standard condition, means this one and this one, they are all under standard condition, all 1 mole per dm cube, they will use or follow this potential. And this cobalt-3 and cobalt-2 now is more positive, so it stay as reduction form, and this one need to reverse. Okay, then you get this. If follow standard condition, you get this reaction equation. Okay, if under standard condition, so means the first equation will reverse and the second will stay. Then the second equation times 2, and you sum up left to left, right to right, you get this equation. And if let's say now under this condition, what happened? If under this condition, we know that the cobalt-3 and cobalt-2 half cell, now the potential is positive 1.702, which is smaller than the hydrogen peroxide half cell. Means now the hydrogen peroxide half cell need to stay as reduction form, and the cobalt-3 and cobalt-2 half cell need to reverse, means this one reversed. Therefore, you get this. Okay, this one stay, and the cobalt-3 and cobalt-2 reverse, you get this. And this one times 2, sum up left to left, right to right, you get this one. So therefore, you get this equation. H2O2 plus 2H plus 2 cobalt-2 positive form 2 H2O plus 2 cobalt-3 positive. Part G. 1. Define enthalpy change of hydration. Enthalpy change of hydration, it mostly need to use the gaseous ion. It's all about gaseous ion that dissolve in water. For example, the aluminum gaseous ion, when it dissolves in water, a large amount of water to form the aluminum 3 solution, the energies that involved or released is the enthalpy change of hydration, and is actually always negative. So the definition is very straightforward. Okay, enthalpy change when 1 mole of gaseous ion dissolve in sufficient water to form a very dilute solution. Make sure it's 1 mole, and it must be gaseous ion. Part 2. Aluminum fluoride is an ionic solid. Complete and label the energy cycle to show the relationship between the delta S solution, the lattice energy, and the hydration enthalpy. Good. This question or this part is quite easy. Where you need to start from? You should start from the gaseous ion, because we know that gaseous ion, it can form the solid. When they combine, they can form the solid. The energies that involve is the lattice energy, delta H LATT. And this salt can dissolve and form the solution. So you just put the arrows here, and of course put aqueous, and this is delta H solution. Okay, form this aluminum's ion and the fluoride solution. And of course the gaseous ion itself, without go through this lattice energy and delta H solution, it can be hydrated. So means the gaseous ion can dissolve in water to form this solution. So the enthalpies that involve is the enthalpies of hydration. So this is a complete energies diagram or energy cycles. Therefore, you need to use this value, right, to calculate the delta H LATT for the aluminum fluoride. Again, try to use this cycle. So we know that delta H LATT plus delta H solution is equal to the delta H of the hydration. So that's why we got this relation. And after that, you need to substitute this value into the relation. In this question, it wants you to calculate delta H LATT, the lattice energy. So you need to calculate the hydration's enthalpy first. You have to combine the hydration enthalpies of the aluminum ion and the fluoride, because it involves 1 mole of aluminum ion and 3 moles of fluoride. So here times 1, here times 3. Sum it up, okay, minus negative 209, which is the solutions of the aluminum fluoride. So therefore, you get negative 5999 kilojoule per mole. Okay, that's all for this question. Thank you.